Have you ever looked at a diagram of an aircraft engine? I mean, it just looks like a total mess, right? A maze of pipes and gears and all sorts of complicated bits. But what if I told you all of that complexity boils down to one powerful and surprisingly simple idea? Let's get into it.
I mean, this is the big question, isn't it? How do you get from a tank full of liquid fuel to a massive metal machine just hanging out in the sky, defying gravity? So let's follow that journey of energy.
In this explainer, we're going to trace that exact path, from the chemical stuff that's locked away inside fuel, all the way to the raw mechanical force that gets an airplane off the ground.
Okay, so let's start at, well, the heart of the plane. And for most smaller aircraft, that heart is a reciprocating engine. It's the powerful muscle that gives the whole system life.
So why did I call it a reciprocating engine? It's actually pretty simple. It's all about the pistons constantly moving back and forth, back and forth. Its only job is to turn the chemical energy in fuel into actual mechanical motion. You can kind of think of it as a series of tiny, perfectly controlled explosions, all working together to get a job done.
So how does this whole thing actually happen? Well, pilots and mechanics have this awesome little phrase for it, and once you hear it, you'll never forget it. Suck, squeeze, bang, blow. This four-step dance is the secret sauce to generating power.
The stage for this little performance is inside the cylinder. And our main actors? Well, you've got the piston, you've got the intake and exhaust valves, and of course, the spark plug. Let's see how they all work together.
All right, here's that dance in action. First up, suck. The piston moves down, drawing in that mix of fuel and air. Then, squeeze. The piston shoots back up, compressing that mixture, really packing it with potential energy. Then comes the best part, bang. The spark plug fires, ignites the whole thing, and the explosion violently slams the piston down. That's your power stroke. And finally, blow. The piston comes up one last time and pushes all the burned gases out. And that's it. Suck, squeeze, bang, blow.
And you gotta realize, this isn't happening in slow motion. This whole four-stroke cycle is repeating hundreds of times every single minute, in every single cylinder, all synchronized perfectly. Each one of those bangs gives a little push to the crankshaft, and all those pushes add up to create a smooth, continuous flow of power.
Okay, so the engine's got its heartbeat down pat, but just like any living thing, it also needs to breathe. That's where the induction system comes in. Its whole job is to get the perfect mix of fuel and air into those cylinders.
Now, there are basically two ways an engine breathes. There's the carburetor system. That's kind of the old school method, which mixes fuel and air pretty early on. Then there's the more modern approach, the fuel injection system. This one squirts fuel right before or directly into the cylinder. It's way more precise, gives you better performance, and, this is a big one, it solves a really critical problem that you can get with carburetors.
And when I say critical, I mean this problem can literally end a flight. Because when you get up to altitude, the air gets cold, really cold. So what happens when the engine's lungs start to freeze over?
This right here is carburetor icing, and it's a pilot's nightmare. Here's the crazy physics of it. As fuel vaporizes in the carburetor, it causes a massive temperature drop. We're talking as much as 70 degrees Fahrenheit. So any moisture in the air instantly freezes, building up ice that can literally choke the engine and cut off its air supply. And the scariest part? This can happen even on what feels like a perfectly warm day.
So if you're a pilot, you are always watching for the signs. A drop in your engine RPM, a loss of pressure, or just the engine starting to run rough. The fix is called carburetor heat. You basically flip a switch that diverts hot air from the exhaust over to the carb, melting the ice and letting the engine breathe again.
Okay, so our engine's running, it's making power. But a spinning crankshaft by itself doesn't move a plane forward. How do we turn that rotational motion into forward thrust? Well, that's where the propeller comes in.
Honestly, the easiest way to think of a propeller is just as a wing that's spinning on its side. I'm serious. Each blade is shaped just like an airfoil, like a wing to create a pressure difference. But instead of generating lift to go up, it generates thrust to go forward, pulling the whole aircraft right through the air. And you ever notice that elegant twist in a propeller blade? Well, it's not just for looks. It's a piece of brilliant engineering. You see, the tip of the propeller is moving much faster than the part near the center HUD. That twist makes sure that every part of the blade hits the air at the most efficient angle possible, generating uniform thrust all the way down its length. So clever.
Now, on many smaller airplanes, the propeller's pitch, or its angle, is fixed. And that means there's a trade-off. You can have a climb propeller, which is kind of like the low gear on a bike. It's fantastic for takeoff and climbing, but you're not going to win any speed records. Or you could have a cruise propeller. That's your high gear, super efficient at high speed,
but it feels really sluggish trying to get off the ground.
All right, we've got power and we've got thrust. Now let's do a quick run-through of the critical life support systems that keep this whole engine running safely. First, the ignition. Aircraft engines have two independent magnetos for redundancy. They generate their own electricity, so if the plane's entire electrical system fails, the engine just keeps on running. It's a huge safety feature. Then there's the oil system. Think of it as the engine's blood. It doesn't just lubricate, it cools parts down and carries away gunk. And finally, the cooling system. A lot of the time, it's as simple as air flowing over these special fins on the cylinders, carrying away all that intense heat from combustion and preventing the engine from, melting.
And that brings us full circle. The official FAA handbook puts it in these formal terms, talking about the conversion of chemical energy into mechanical energy. But at the end of the day, what is it really? It's just suck, squeeze, bang, blow. That is the simple, elegant principle at the very core of all this complexity.
For over a century, the reciprocating engine has been the beating heart for countless aircraft. But technology is shifting, right? We've gone from pistons to jets, and now we're starting to see electric and hybrid power. It really makes you wonder, what's the heart of the plane going to look like a century from now?